If a snowball melts so that its surface area decreases at a rate of 1 square centimeter per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. Okay, so we have a melting snowball here, which is a quintessential related rates example. Let's check out our steps to see how to approach it. Step 1 essentially says to read the problem and deeply understand intuitively what's happening, draw a picture, and write down your givens and goals. Okay, so let's all imagine what it's like for a snowball to melt. An analogous problem might be a balloon deflating, a spherical balloon deflating. We can draw a picture of this. There's our spherical snowball. Okay, so this is a sphere, and we have our radius here, which diameter will be twice that distance. Let's clearly keep track of what is given in this example and what our goal is. That helps us kind of narrow it down and focus on the math rather than all these words. So given, the surface area decreases at a rate of 1 square centimeter per minute. This gives us dA dt equals -1 centimeter squared per minute. And then it asks us to find the rate at which the diameter decreases. So our goal is d, well, let's call this capital D for diameter, otherwise it's weird. dd dt, it gets very strange very fast. So d, capital D dt. When the diameter is 10 centimeters. Okay, that completes step 1. Let's check back in with our steps for step 2. Step 2, write an equation that relates the various quantities of the exercise. If necessary, use geometry to eliminate a variable. Okay, well, we should know the equation for the surface area of a sphere. A equals 4 pi r squared. A quick way to remember this, assuming that you know the volume of a sphere, 4/3 pi r cubed, which you should know, the derivative of volume with respect to r always gives you the surface area, 4 pi r squared. So that's a quick way to just remember one quantity, the volume, and then remember that the derivative gives you the area, assuming you can remember how to take derivatives, which hopefully you can. Okay, we're almost there. We related area and radius, but we need area and diameter since those are the two quantities we're talking about in our givens and our goal. So let's use a little bit of geometry. It's not much geometry, but note that diameter is twice the radius. So that tells us that the radius is diameter over 2. Plug that in right here, and then we can take the derivative. So the area is 4 pi times d over 2, quantity squared. So that gives us area is actually pi d squared. So these are related rate exercises, and I like to think of this as the relate step. We've related them, and now we have the rate step, which is where we take the derivative. And we find that's step 3 if we check back in with our steps. Step 3, use the chain rule to differentiate both sides with respect to t. Okay, so we're taking d by dt of both sides here, so dA dt equals, over here we have 2 pi d, that's the power rule, and then the chain rule d dt. Because we're taking the derivative with respect to time and not with respect to d, we have to tag on this extra chain rule step. This is simply the chain rule. If it were u, we'd have to tack on a u prime. It's the same idea. Back to our steps. Step 4 says substitute known values and solve for the desired quantity. Okay, well, our goal is to solve for d dt. So let's go ahead and solve our equation for that. We have d dt, a little bit of algebra here, d is dA dt divided by 2 pi d. And we want to evaluate this when d equals 10 centimeters. Okay, so, well, dA dt is -1. I'll leave the units out to the very last. Over 2 pi d is 10. So this gives us -1 over 20 pi. And units are, let's see, this is derivative of diameter with respect to time. So it's going to be centimeters distance over time per minute. Running right out of room there. There we go. 1 over 20 pi. -1 over 20 pi. So it's decreasing. Step 5, check that the answer is reasonable. Well, is this reasonable? It's hard to tell without actual numbers, and even if we plugged in numbers, it would be kind of hard to tell. So sometimes step 5 really jumps out that something's off, so maybe we should take it that way. If something's really far off, something's wrong. If this was 1,000 centimeters per minute, then we'd pause and go back and check our work. So I think this sounds reasonable. One interesting point with this, let's imagine a snowball melting, so it's shrinking. dA dt is constant, that's at -1, so this is constant. And look what happens to this rate of the diameter. So we're imagining this thing getting smaller and smaller and smaller. As the diameter gets smaller, since that's in the denominator, the rate that the diameter changes with respect to time gets larger. So you can imagine a shrinking snowball. When it's huge and melting, the diameter is changing at a very low rate because it has so much surface area. And then as it gets smaller and smaller and smaller, that diameter has to speed up. So you can imagine, if you're just looking at the width of the snowball, it's going to get smaller faster and faster and faster, to where at the very end it's going to vanish very quickly. So if you really dig deep into these, you can get a good idea of the physics of what's happening by deeply examining the equations that you end up with.